Hello, and welcome to another video in which I will explain how to simplify resistances by looking through two terminals. So first things first, this is a different, a little bit daunting kind of circuit. However, if you remember the parallel and series connection, which I will show here. So I have here one resistor, here I have another resistor, and let's say that I put a wire here in between, and then I put nothing on the other side. Let's say that this is just connects to something else. Then we can see that this terminal of this resistor is connected to only one terminal of the second resistor. So they only share one terminal, in this case, one connection. So this means if there is, let's say that this is open in between, they are connected in series. Now, for a parallel connection, we need to make sure that both terminals are connected by only wires. So in this case, this terminal of R1 is connected to this terminal of R2, and there's nothing in between. Now this other terminal is connected to this other terminal between R1 and R2, so both of the connections are only using wires. So in this case, this will be a parallel connection. So the point here is to identify first which resistors can be simplified right away by looking if they are in series or in parallel. So this circuit will help you identify those. So now let's go back into the problem. So right away I can see, for example, there's many ways you can tackle this problem. So let's say, for example, I have this 16 ohms, right? And I can see that these are two terminals from the 16 ohms. Now, if I were to look, let's say, at the terminals of this 2 ohm resistor, I can see if there's a connection, a parallel connection, let's say, between the 16 and the 2. Well, this, we know these two terminals are connected just by wires, but this one is not. So if there's a resistor in between, then they are not in parallel. Now for the next one, we have that only one terminal is shared. So yeah, this means that this would be quote unquote a connection in series apparently, but the problem here is that there is another resistor in between these two terminals. So there's an extra connection that does not allow us to combine them in series. So right now, we cannot combine the 16 and the 2. But we can see here, let's say we go to the 48 resistor here. Notice that the 16 ohms and the 40 ohms terminals are connected here by just a wire. And then this 48 is connected also by just a wire to 16. So both of these are actually in parallel. So you may see, oh, but what about these open terminals? Well, the thing is that these two terminals are the same, so they are shared. However, since it's open and we are looking into the terminals, then this is a valid connection. So what I will do here is I will combine the two resistors in parallel. So this is equal to the product over the sum. So 16 plus 48, which will give us, so it's 16 times 48 over 64, which will give us 12 ohms. So now I get to combine these two in parallel. So let's go to our problem here. We can see clearly now that the 16 and this 48 are in parallel. So we will combine them, and notice how the resistance, the new resistance will be combined. We will see that one of the resistors slides, quote unquote, onto the wire and then creates one resistor out of those two. So we'll put here 12. So we submit and we are correct. So notice here that this 12 ohms, this new resistor, has taken the place of the 16 ohm resistor, and this 48 ohms has been replaced by an open circuit, which if you looked at the other videos with simpler circuits, makes sense that it has been replaced by an open circuit because it's in parallel. So now we have this new circuit. Now, we might be tempted, again, to combine in parallel by looking at this 3 ohms and this 6 ohms, because we can see that they are connected by its terminals here, this 3 and this 3, and the terminals here about the 6. Both of them are just connected by wires. So one of them is going to be replaced by the new value, while the other is going to be an open circuit. So we have a good connection there. It's valid. Both of them are in parallel, so it's going to be 6 in parallel with 3, which will then give us a value of 2 ohms, right? So 6 times 3, 18, over 9 is 2. So then we select these two already, and then we will connect them or combine them in parallel. So I will combine the 6 and 3 in parallel, will give us 2 ohms. One of them is going to become an open circuit. The other is going to become the new value. In this case, notice that the 3 ohm resistor here was replaced by the 2 ohms, and then we made an open circuit, which means it goes away. So now it makes things a little bit easier, right? So we can now clearly see that these two 2 ohm resistors are in series, and we can combine them because one of these connections, so let me give you the 2 terminals. These are the 2 terminals of the 2 ohms. One of them is in series. The other terminals are not, but they are connected to something else. So this is a series connection. So then we can combine them to create a 4 ohm resistor, and one of them is going to be replaced by a wire, while the other will be the new value. So let us combine them. So combined in series, which will give us 4, and it is correct. So now I will clear all the drawings, and now it's getting a lot simpler, right? So same thing here. We go again, remember, we always go from the furthest resistor, or at least in this case, the one that we can clearly simplify by looking at the parallel connection. So in this case, this 4 ohms, same thing. We draw the terminals of the 12, draw the terminals of the 4. By the way, once you get a lot of practice with this, you will immediately see the parallel and series connections, and you won't need to, explicitly draw every single time. I'm just showing you this so that you can see step by step and the reason why we combine these resistances. So now we know that these 12 and these 4, they are in parallel because they share both terminals. So we will combine them in parallel. So then it's going to be 48, so it's going to be 12 times 4, 48, over 16, it's going to be 3. So one of them will have the new value, while the other will have the open circuit. So now we can see that our circuit is almost finished. So now we can see that this 3 ohms is in series with this 9 ohms. Why? Again, we draw the terminals. And then we can see that this connection is shared, but the others are not, right? Because they go down to the open terminals. So I will combine these in series, and then I will do the sum, which is going to be 12. And then finally, we have our circuit. So we have finished it. Now, one thing that I want to make clear is that there are many ways of solving this circuit. So what I will do here is I will solve the same problem again. And this time I will make a different connection. So the first one I made was a 16 in parallel with the 48. Now you may be thinking, well, can I do the parallel between the 6 and the 3 first? The answer is yes. So let's do that. So in this case, we will have a 3 ohm resistor here directly in parallel with the 6. You may have noticed, because these terminals are shared by both resistors and there's only wires connecting them. So this is a parallel connection right away. So let's simplify by doing the 3 and the 6 first. We already know that it's going to be 2 ohms. So then let's do the 2 ohms. We combine them in parallel, and then one of them becomes an open circuit, the other becomes the new value. And then we can see that even here, look, we can combine already the 2 ohms here in series, because again, they only share one terminal. So we have here 4. One of them becomes a wire, the other becomes a the value. So now notice here that the 4 again now has the parallel connection with the 16. So it's a little bit different, but it's the same process, right? So there's only wires connecting them. So now the 4 is in parallel with the 16. So if we do our simplification, is going to give us, so 16 times 4 is 30, 64 over 20. So this is going to give us 3.2, I think. I'm not 100% sure. Let me see. So I will combine these two in parallel, which will give us 3.2. So let's submit this answer. And yeah, okay, it is correct. Sometimes my math is not correct 100% of the time. And then now we can see that this 3.2 ohms is in parallel with the 48. Both terminals are being shared. So now we will combine them in parallel. So we will combine the parallel. So it's 48 parallel with 3.2. So it's the product over the sum over 51.2, which is the sum. So it's 48 times 3.2 over 51.2. So this will give us 3 ohms. So in this case, we will combine this 3.2 and this 48 in parallel, and the equivalent resistance will be 3. So we submit, and we have the final resistor values, which if you notice, they are the same. So now we have a 9 and a 3 in series. So then we will have 9 plus 3 equals 12. So we will combine these two in series, and we see that we did a different procedure. Let me just erase all drawings. We did a different procedure, but we arrived at the same answer. So as I've said before, there are many ways of solving this. The thing is for you to keep practicing until you have mastered some sort of, let's say, pattern recognition or the underlying concept, right? Which is, okay, which ones are in parallel, which ones are in series, which ones I can combine, which ones I cannot. And you can only get this intuition when you practice enough. So yeah, this is how to combine resistances as seen by two terminals in 4 loops. And yeah, hopefully this video helped you. If you have any questions or comments, please let me know. And thank you for watching the video. Keep practicing.